LDA expects word counts. Feeding the same text to NMF changes what a topic means. You'll compare NMF on TF-IDF with LDA on word counts, revealing topic words, component sparsity, and agreement in dominant topic assignments. I'm Professor Pi, teaching AI foundations with simple Python. Topic models help when a pile of articles has no useful labels. They can surface broad themes for browsing, organizing, or checking what a collection contains. Scikit-learn is a good fit because it gives us text features and both models in one familiar workflow. A repeated word can mean different things depending on how we represent it. NMF works well with TF-IDF, where common terms lose influence. LDA works from word counts, where repeated tokens are evidence that a topic is present. We will use one tiny corpus with clear space and cooking themes. That makes the comparison easy to inspect before the same pattern is used on a larger collection. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need a shared set of documents that both models will see. This snippet creates 6 short documents with 2 easy-to-see themes. Topic models can look convincing, even when the input is poorly designed. So this balanced corpus makes mistakes visible before complexity grows. The first 3 documents repeat space terms, while the last 3 repeat cooking terms. Anchor words give both formulations enough signal to separate the groups. These could represent short news articles from 2 sections in a larger collection. The output confirms the document count and displays the first text. That establishes the shared corpus used by every later step. So any later difference comes from representation or model behavior. The documents are fixed, but each model needs numbers rather than raw text. This code builds count and TF-IDF views of the same corpus with scikit-learn. Using one matrix for both models can hide an important modeling choice. CountVectorizer.fitTransform records token frequencies. TfidfVectorizer.fitTransform reduces the influence of terms that appear across many documents. The variables xCount and xTFIDF therefore have matching rows and columns, but different numerical meanings. Keeping both views lets each model receive the representation suited to this comparison. The output shows identical matrix shapes, confirming that only the weighting changed, not the documents or vocabulary size. That gives us a fair starting point for comparing topic results. TF-IDF is ready, so we can ask NMF to find a small set of non-overlapping word patterns. This example fits scikit-learn NMF to the TF-IDF matrix and extracts each topic's strongest word. NMF approximates xTF-IDF with 2 non-negative factors. NMF.doc contains document topic weights, while NMF.components contains topic word weights. The n-components value fixes the requested topic count. Increasing it can split broad themes into narrower ones, while too few topics can blend unrelated ideas. Random state makes the fitted result reproducible. Calling argmax on each component identifies its largest weight, and sorted removes arbitrary topic ordering from the display. The output surfaces recipe and rocket as the strongest anchors, showing that NMF recovered the 2 intended TF-IDF themes. For more practical Python and AI lessons, you can subscribe and keep building these foundations. NMF found clear themes, but LDA needs the original count-based version of the text. This snippet fits scikit-learn LatentDirichletAllocation on raw token counts. LDA treats xCount as observed word events and estimates distributions over topics and words, so count data matches that probabilistic formulation more directly than TF-IDF weights. LDA.fitTransform returns normalized document topic distributions in LDA doc. Each row says how strongly a document belongs to each topic. LDA.components stores topic word pseudocounts, which are weighted evidence for words inside topics. As with NMF, argmax finds each topic's strongest word, and sorted makes the presentation independent of topic numbering. The output shows the same two anchors, although LDA reached them through a different matrix and modeling assumption. Matching top words is useful, but it does not reveal how the models distribute weight internally. This code compares scikit-learn NMF and LDA beyond their matching headline words. Values below 1e⁻⁶ reveal that nmf.components_ can contain effectively 0 weights, while LDA.components_ remains dense because its entries represent positive pseudocounts. The code then names each component by its strongest word, converts NMF doc and LDA doc into dominant topic assignments, and counts agreements without relying on arbitrary numeric topic IDs. NMF is useful when sparse, parts-based themes aid interpretation. LDA is useful when probabilistic mixtures are the goal. The output shows different component sparsity despite matching assignments for all 6 documents. When a document genuinely mixes subjects, LDA's document topic distributions can be especially useful. A news article about a rocket launch and a meal prepared for the crew may deserve meaningful weight in both themes. NMF can still express mixtures, but its sparse structure often makes the strongest theme easier to explain to a human reviewer. On larger corpora, inspect the top words and a sample of documents for every topic. A clean-looking number is not proof that a topic is meaningful. This example shows that topic agreement can hide major differences in representation and model assumptions. NMF emphasizes weighted word patterns, while LDA models repeated word events as probabilistic topic evidence. Try changing n_components and inspect whether the 2 clear themes split into smaller, useful topics or become noisy. You can also adjust the TF-IDF settings and see how stronger downweighting changes NMF's leading words. What practical topic modeling question would you like to explore next? Leave it in the comments, and subscribe for more clear Python data science lessons.